Bioethanol derived from sugarcane molasses has rapidly emerged worldwide as a highly viable, scalable source of renewable energy. For a modern industrial model, the baseline objective is straightforward. Build a facility capable of producing 100,000 liters, or 100 kiloliters, of bioethanol every single day. Achieving that volume is not restricted by the limits of modern distillation technology. The real challenge lies entirely in supply chain mathematics. Industrial distillation is a continuous chemical process. A plant like this is designed to operate roughly 330 days out of the year, leaving about a month for annual maintenance. Agriculture, however, operates on a very different clock. Sugarcane harvesting and the mills that crush the cane to produce the molasses feedstock typically only run during a strict 150-day dry season. This creates an immediate operational paradox. A continuous chemical process relies entirely on an aggressively seasonal raw material. Designing a successful, integrated facility requires a first principles calculation of the infrastructure needed to bridge that 180-day gap, where the harvest has stopped but the chemical plant is still running. Failing to calculate this operational asymmetry up front guarantees the construction of a starved, stranded, multi-million-dollar asset. As this flow diagram illustrates, the foundational conversion metric relies on total fermentable sugars. 1 ton of molasses yields approximately 250 liters of ethanol. To hit the 100,000-liter daily target, the plant must consume 400 tons of molasses every 24 hours. Multiplying that daily intake by the 330-day operating calendar reveals a massive requirement: 132,000 tons of molasses annually. Here is where the temporal bottleneck takes effect. The upstream sugar mill must produce that entire 132,000-ton volume within its compressed 150-day window. Dividing the annual need by those 150 days forces the mill to output 880 tons of molasses every single day it operates. But molasses is a byproduct. It accounts for only about 4.5% of the total raw sugarcane weight processed by a mill. Producing 880 tons of molasses at a 4.5% yield means the upstream sugar mill must crush roughly 20,000 tons of raw sugarcane daily. In the industry, this metric is known as TCD, tons of cane per day. A 20,000 TCD mill is a colossal industrial facility, operating far beyond the scale of a standard regional factory. Because the sugar mill only crushes for 150 days, the ethanol plant also requires massive physical infrastructure, specifically extra steel tanks, to hoard enough molasses to survive its 180 days of idle time. This temporal mismatch creates an unavoidable multiplier effect. Feeding a seemingly moderate, steady-state chemical plant mathematically demands one of the largest classes of sugar mills possible. Moving from industrial capacity to agricultural reality, running a 20,000 TCD mill requires harvesting 3 million tons of cane annually. Based on average productivity of 70 tons per hectare, that volume necessitates nearly 43,000 hectares of active plantation. Once that crop is processed and the downstream distillation is complete, the chemical plant yields a high-volume, toxic liquid byproduct known as vinasse. For every single liter of ethanol produced, the process generates up to 12 liters of vinasse. At our baseline capacity, that is 1.2 million liters, or 1,200 cubic meters, of liquid waste every day. Standard industrial disposal is impossible. The sheer volume and the liquid's aggressive biological oxygen demand would destroy local waterways. The project outline dictates a mandatory structural solution: the construction of a massive anaerobic biogas reactor to digest the daily vinasse output. This reactor treats the waste and converts it into methane gas for the mill's power generation, while the remaining residue is concentrated into liquid organic fertilizer to be returned to the sugarcane fields. Implementing this zero-waste loop is a strict operational necessity. Without it, the facility would physically drown in its own byproduct. With a requirement of 43,000 hectares, an investor might assume they can simply acquire the cheapest, most remote land available. However, site selection documentation shows the ethanol distillation and cooling processes require a massive daily water intake, drawing between 1,000 and 1,500 cubic meters a day. That specific volume mandates placing the facility directly adjacent to a major permanent river or reservoir. Furthermore, fuel-grade bioethanol is a highly flammable product, which means the site must also sit on a Class 1 heavy transport route to manage the outbound logistics safely. Finally, processing 1.2 million liters of biological waste daily generates a severe odor, forcing the site to maintain a large buffer zone away from populated areas. Finding a site that combines massive contiguous acreage, river access, heavy highway infrastructure, and deep isolation severely limits the viable geographic coordinates for the project. All of these derived physical requirements ultimately materialize on the balance sheet as capital expenditure, or CAPEX. This chart breaks down the total investment. The core 100 kiloliter ethanol distillation plant alone requires between $25 and $35 million, but the 20,000 TCD sugar mill required to independently feed it demands an additional $200 to $250 million. Adding supporting infrastructure requires $10 to $15 million for biogas waste treatment and $3 to $5 million for storage tanks. The total project CAPEX with necessary integration eclipses $300 million, or over 4.5 trillion rupiah. This is the CAPEX illusion. Controlling the feedstock for a nominally cheap chemical byproduct forces an investor to fund a massive, high-risk upstream monopoly. For investors unable or unwilling to deploy $300 million, the strategic recommendation is a hybrid supply model to mitigate the capital requirement. This alternative scales down upstream infrastructure. Build a 10,000 TCD mill to handle half the load, cutting initial costs, then source the remaining 50% of molasses through external agreements with existing mills. While an integrated system guarantees operational security, mastering supply chain mathematics and forging strategic partnerships makes these agro-industrial megaprojects financially viable.